Hi there, how are you going? Welcome to this Engineering Mechanics lecture video. Let me share my screen and we'll get started. Okay, so in this lecture video, we're going to look at the moment of a couple. So in the previous lecture video, we looked at the moment of a force. So we learned that forces not only have a push and pull effect on a body, but they'll also cause a body to turn or rotate or twist. And we learned to calculate the moment of a force, which is the force times the perpendicular distance to the point about which we're trying to calculate that turning effect or that moment. So today we're going to look at the moment of a couple, and we're going to learn to firstly define what a couple is and then to determine the moment of that couple. Just a couple of very simple applications, I guess, taken from the Hibbeler textbook. So if we've got this wheel here shown in the picture, and we require a torque or a moment of 12 Newton meters to rotate the wheel, which one of the two grips of the wheel above will require less force at each hand to rotate the wheel? Now, this is intuitively reasonably obvious, I hope. The further, and you would have experienced this in real life, so the further you put your hands apart, the less force you have to apply. Okay, so where in the left-hand picture, where the hands are 0.4 meters apart, will require less force to rotate that wheel than in the right-hand picture where we've got 0.3 meters between the two. All right, so in each case, though, what do you calculate will be the force required? So just stop the video and do that calculation quickly and see what you come up with. So if we need 12 newtons, so in the left-hand picture, we'll need 30 newtons, and in the right-hand picture, we'll need 40 newtons. Okay. All right. So if you didn't get those answers, don't worry too much. In the coming slides, we'll explain why the answers are what I gave you. Okay. So in the left-hand one, it's 30 newtons, and in the right-hand one, it's 40 newtons. Okay, another simple example that you may have experienced in your life, changing the wheel on your car. And if we have a typical crossbar lug wrench like this, trying to loosen that nut, what's the effect of changing the dimensions that are shown on there, A, B, or C? All right, so if we change A and B, so if we make both A and B bigger, as we discussed before, then the force that we need to apply becomes less. If we make A and B smaller, then the force that we need to apply becomes greater. Now C in this example, so that's the length of this part of the wrench, that's not going to affect how much force we need to apply. Okay. If we had different forces here, if this force was not equal and opposite to the force on the left-hand side here, so if this one was bigger than this one, then we would get a bending of this part of the wrench, and C would influence how much bending we get. Okay, but that's for a later topic. All right, so moving on to define a couple. So a couple is simply defined as two parallel forces. So over here we've got force F and force minus F, two parallel forces with the same magnitude, okay, same magnitude F, but opposite in sense. Okay, so the one at the top is going to the left, one on the bottom is going to the right, and they're separated by a perpendicular distance D. Okay, so this is what's known as a couple. And we can look at the right-hand rule here. So if we look at something rotating anti-clockwise, so our fingers going around here, if we're looking down here, going anti-clockwise, the vector moment is along the direction of your thumb. Okay, so don't worry too much if you don't get that. We'll, for now, just consider only two-dimensional problems or planar problems, and we'll look at three-dimensional problems in a later lecture video. Okay, so as we've set up in words, the moment of a couple is defined as these two forces, equal and opposite, separated by a distance. If we want to actually calculate that moment, then the moment is equal to the force times the distance between the two forces. So the magnitude of each of, or either of the two forces times the distance between those two forces. Okay, so hopefully now if we go back to our example that we looked at here, so the moment is equal to force times the distance between the two forces. Okay, so I said here we've got a distance of 0.3 to get 12 newtons. 30 times 0.4 will be 12. I think I've done my maths right. If I haven't, I've got to do this video again. Right? And here, 40 times 0.3 will give us 12. Okay, so the other thing to note here, and a very important thing to note, is that the net external effect of a couple is that the net force is equal to 0. Okay, because these two forces are equal and opposite, right, same magnitude but opposite in directional sense, is that the net force is equal to 0, and the magnitude of the net moment, as we've just discussed up here, is equal to force times the distance between. That may be a little bit confusing to some. I know that some students are unsure about that. Think, well, hang on, there's two forces. Why are we only taking one force? Hopefully this little exercise will help clear that up. If we look at our couple here, so I've got a couple, a force here acting to the right, and the same magnitude force acting at a distance d to the left, parallel to the original one. If I now say, let's choose any arbitrary point on the page. Okay, so I've just chosen this point here, point O down here. And I've defined that location as a distance A from this bottom force, or this lower force. If I now calculate the moment of these two forces about point O, right, and this time I'm using clockwise as positive, just because, no particular reason. We could have taken anti-clockwise as positive. So in fact, why don't you do that as an exercise for yourself and see that you get the same answer. Right? Take anti-clockwise as positive. But here in my working out, I've taken clockwise as positive. So M is equal to force times the perpendicular distance to the point that we want to know the moment about. Okay, so the moment about point O of this force is the magnitude of the force times D plus A, okay, which is what I've got over here. And then the moment of this force, the lower force acting to the left, its moment about point O is simply F times A, and because we've treated clockwise as positive, right, we have a negative sign in front of this term in the equation. Okay, so if we do our maths here, we can see we're going to get F times D plus F times A minus F times A. Okay, so we end up with F times D. Right, and we would have ended up with this result no matter where we took moments about. Okay, we could have put point O up here, we could have put point O out here, we could have put point O in the middle. All right, so let's think about what would happen if we put point O in the middle here, where I've got the laser pointer, and do our maths. All right, so taking clockwise as positive again, we would have F times D over 2 plus F times D over 2. So 2 times F times D over 2 equals F times D, okay? So no matter where we choose our arbitrary point, the net moment of a couple will be force times distance between the two forces. So what this tells us is that we can place our couple anywhere on a body and it will have the same external effect. Okay, and I think I've summarized that down here. Right. Since the moment of a couple depends only on the distance between the forces. Okay, so up here, we took any arbitrary point, and no matter where we put that arbitrary point and calculated our moments, the net moment was simply force times the distance between the two forces. All right. So what that tells us is that the moment of a couple is what we call a free vector. Okay. Now that vector is actually out of the page, or in this case, because we've got a clockwise moment, will be into the page. Nevertheless, it's a free vector. Okay, we can put our couple anywhere we like, and it will have the same effect. So another way of thinking about this, taking an arbitrary point here, is if I get my pen, right, and I put my forces like this, F, and I do, whoops, a bit hard to draw with the mouse, and that's, whoops, D here. Okay, so if I do put my two forces the same as I've got over here, let's go back to my laser pointer. Right. This is equivalent to this in terms of the external effect on the body. Okay. Now, we need to be careful because it's only the external effect. Right? If we think about a structure, something like this, supported in my left hand. Let me stop share for a minute. All right. If I take this little structure here and I support it at one end, and I apply a couple. So with my two fingers, I'm going to apply a force downwards and an equal and opposite force upwards. Okay, so that's a couple applied here. Now I can apply that same couple here, right? And what I need to do with my support in my left hand doesn't change. Okay, so that's what we mean by the same external effect. So I can apply my couple here, or I can apply my couple here, right? And what happens in my left hand doesn't change. But what does change is the shape of the bending of the stick. All right, so if I apply my couple out at the end, the whole stick is bending. Okay, so we've got bending, deformation throughout the length of the stick. But if I apply the same couple here, I get bending between my two hands, but from my right hand out to the free end here, right, that doesn't bend as such. There's no bending between here and here. It's just rotating as a straight line. Okay, so that's what we mean by internal and external effects. The other thing, if we're doing dynamics, whether we apply the moment like this or whether we apply the couple like this, right, the effect on the body in terms of how it flies off would be the same. Let me share my screen again. Next screen. So now let's have a look at a bit of an example problem. So we've got here, in our given information, two couples act on the beam. Okay, so we're told that we've got two couples act on the beam and that the resultant couple is 0. And we're asked to find the magnitudes of the forces P and F. So we've got these two forces here, P and F, and we want to know what the distance D here is for the resultant couple to be 0. All right, so let's think about how we might solve the problem. So first of all, right, the information that we're given is that we've got two couples. Okay, so from our definition of a couple, two forces, equal and opposite, separated by a distance. So the forces must have the same magnitude, so we can easily tell straight away that our force P here is going to be equal to 500. Right, so that's one of our couples, and the other couple is 300 and this force F here. So we can do that straight away. Then usually when we're calculating moments, it's usually easiest to find or to resolve our forces into components. If we've got forces at angles, usually it's easiest to resolve them into components rather than to try and find the perpendicular distance between these two forces. Now you can do that, and some people are better than others at trigonometry and might be able to more easily find a distance D here between these two forces. But seeing that in the problem, we want to know this distance here, D, we know this vertical distance here, 0.2 meters. So it makes more sense, or for most people, it would be easier to resolve these forces at 30 degrees and 60 degrees, which is the same as 30 degrees in here, resolve them into components. Then we can determine the net moment by writing our equations and then equate the net moment to 0 to find d. Okay, so there's a distance, an unknown distance here, d. When we calculate the moments, that term will appear in that equation. We set that equal to 0 because that was what we were told in our given information up here to solve for that d. All right, so looking at our solution, as we discussed before, from the definition of a couple, we know that this 500 and this force here, P, form a couple, equal and opposite separated by the distance, parallel forces. So P is going to be 500 and F will be 300. Okay, so the 500 and the P, the force P here, are both horizontal, so we don't need to put those into components. But we can resolve this force here at 30 degrees into horizontal and vertical components. Okay, so looking at just this force here, 300, its vertical component is the adjacent side. So if we have a little triangle here, my bad drawing with the mouse again. So I draw my triangle here. Right, there's my right angle triangle. The adjacent side is this side. Okay, the angle here is 30 degrees. So our vertical component will be 300 cos 30. Our horizontal component is the opposite side here. So that's the sine of the angle. So 300 sine 30 will give us our horizontal component. Note that the component of that force actually acts down here. Right, sorry about my bad mouse drawing. Right, so some of you may have drawn a component up here like this at the top. Try and get out of the habit of doing that. Try and draw your component down here where it's actually acting. Okay. The reason for that is that when we draw it down here, it's actually acting through its correct line of action. Okay, so when we go to calculate the moment about point A in a second, we've got this correct distance here. We don't have a force up here, some distance above there. So it was given that the net moment equals 0. So if we do our sum of the moments, so we have a couple here, right? So we have one couple, and we remember that the definition of a couple, the magnitude of a couple is the force, or the magnitude of one of the forces times the distance between. Okay, so that's what we've got here. And here in my equation, I've shown that we've got we're considering anti-clockwise as positive. Right, so this moment here is going clockwise. If you're not sure, right, don't be afraid to just pick up something and apply the force and rotate it and see which way it's going. Okay, so you looking at this, it's actually looks like it's probably looks like it's going clockwise, anti-clockwise on the screen. For me looking at it, it's going clockwise. Okay, so I can see this rotating clockwise. So that's a negative moment. Right, so that's why I've got this negative sign here. All right, here, instead of treating this as just one couple, what we've done is to treat it as two couples. All right, so again, there we go. So we've got that force, which is our horizontal component that we calculated here. And we've got one up here. And then this same magnitude force of 300 resolves into component there and component like that. All right. Okay, so now we've got, instead of one couple with the 300 Newton force at the angle of 30 degrees, we've got two couples. The couple that's formed by the horizontal component at the top and the horizontal component underneath, separated by a distance of 0.2. Right, so that's what we've got in this term here. And again, we can see that that will be tending to rotate clockwise. So if you just look at point A, for example, right, this force here will rotate clockwise about point A. Okay. And our other two forces, so the vertical components of the 300 Newton forces, separated by a distance here d, okay, 300 cos 30, so we work that out up here, times d. So we now have one equation, all equal to 0, right, because we were told in the problem that our net moment was equal to 0. Right, so now we've got one equation, one unknown, we can solve for d. And that gives us 3.9645 meters. Okay, and we can round that up to 3.96 meters. All right, so let's think about this a little bit more. Because I know some students have problem with couples and moments. Let's assume we don't know about couples. Okay, and all we've got is this structure with 4 forces acting on it. Okay, and what we're going to do is to calculate the net moment of these forces about some other point. Okay, so we're going to use here point B. And we're going to use the forces that we calculated previously. Okay, so P is 500 and F is 300. Okay, so we've again got two couples applied. Right. Now, because in the problem, the distance between point A and point B wasn't given, I'm just going to assume some distance, right? Just make it up. Right? So I'm going to say the distance between A and B is 1 meter. Right? So now, going back to our the previous lectures work where we first looked at moments and calculating moments about a point, we're just going to look at these 4 forces and calculate the moment of those 4 forces about that point B. And ignore the fact that we now know about couples and know what the moment should be. Right, so if we take moments about point B, so firstly, let's look at this force here, 500 newtons. Right, so that force here, its line of action passes through point B. Right, so its perpendicular distance from point B is 0. Right, so that's why we got 500 times 0 here. Then we've got our force P down here. Its moment about point B is force times perpendicular distance. So perpendicular distance between the line of action of the force and the point about which we're taking moment. So the line of action of this force, if I can do this, the line of action of this force is along here, right? So its perpendicular distance up to here is 2. And it's tending to rotate around in this direction, right? About point B, yeah? So we've defined anti-clockwise as positive, right? So that's why we have a negative here. Okay, the next term. So we've got our 300 cos 30. So we know that that's, okay, so there's our component, this 300 cos 30. Its perpendicular distance from point B is the distance 1 from B to A that I defined, and the distance 3.96 or 9645 that we calculated previously. Okay, so D plus DAB is its moment effect, tending to rotate this thing. Right, if we look at point B, so it'll be pushing upwards, tending to rotate anti-clockwise, tending to rotate around in that direction. Okay, so that's anti-clockwise. So we have positive out the front here. Then we have the horizontal component. So the horizontal component of this 300 force here is out here. So that was our 300 sine 30 that we calculated previously. its perpendicular distance, right? So its line of action of this force is along here. Perpendicular distance to point B is this distance here. So if we assume that point B is halfway between these 2 points, then that's where this, that's where this 0.1 has come from, okay? And it's tending to rotate around clockwise, so therefore negative in front. All right, so then we've got the force down here. So we've got a component down here and a component this way. All right, so this vertical component here, this one here, 500 sine 60, or if you like, this angle in here is 30, so not 500, F sine 60, or if you like, F cos 30, times its perpendicular distance to B will be the distance DAB. And this horizontal component, F cos 60, or if you like, F sine 30, times 0.1, tending to rotate clockwise about point B. Right? So they both tend to rotate clockwise about point B, so they're both negative. Right, so that's calculating the moment of each of these 4 forces about point B. Right, so if you put in all the numbers that we've got up here, you should see that this is equal to 0. All right, so that was a bit long. Hopefully going through it slowly like that has cleared up things for you and not made things more difficult. If there's any questions, please bring them to class, and we'll discuss them then. All right, so let me stop share. All right, so that's it for now. Hopefully that was helpful, and I'll see you in the next lecture video. Bye for now.